Welcome. The webinar will start in a few minutes. Welcome. The webinar will start in a few minutes. Welcome. The webinar will start in a few minutes. Welcome. The webinar will start in a few minutes. Welcome. The webinar will start in a few minutes. Welcome. The webinar will start in a few minutes. Welcome. The webinar will start in a few minutes. Welcome. The webinar will start in a few minutes. Welcome. The webinar will start in 30 seconds. Thanks for joining us today for our webinar, Best Practices for Software Verification under ISO 26262. I'm your host, Bethan Holmes, Marketing Executive here at QE Systems. Today we're going to discuss how our industry experts employ these best practice ISO 26262 software verification techniques to shorten time to market and increase the ROI of software verification activities. Weighing in on this topic are Pierre-Henri Stanek, Cantata Product Manager here at QA Systems, Gudrun Newman, Functional Safety Team Leader from SGS TUV, Chris Clark, Senior Manager at Synopsys for Global Solutions and Automotive Software and Security, Steve Niemer, CTO of LHP Engineering Solutions, and Anne Packery, Functional Safety and Cybersecurity Manager from Frazier Clarion. Please note that you'll be muted throughout the webinar. If you have questions, do feel free to type them into the question window at any time. To open this, use the orange arrow in the top right of your screen. We will answer them during the Q&A portion after the discussion. The webinar is being recorded and we will send you a link to that afterwards. Before we go any further, so that we can best understand our audience today, please answer the 3 questions in the pop-up on your screen. Click Submit when you are done, and we will show the results in the Q&A session at the end of the webinar.
Thanks for that intro, Bethan. I'm Adam Mackay, Integrations Manager at QA Systems. During our webinar today, I'll be logging any questions that come in and feeding them to our panelists at the end. But as Bethan said, we've got a few questions to get us started. So let's put those on the screen. So our first question is, which is your biggest unit testing challenge? I'll leave this on the screen for around 30 seconds to give everyone a chance to respond, and we'll revisit the results at the end. That's great. I can still see some responses coming in, so just a few more seconds. That's great. And our second poll today, who in your organization is responsible for functional safety? Again, I'll leave it for about 30 seconds to get some reasonable number of responses. So that's great. Thanks for those responses. And the final question in our poll session is, what is the biggest barrier to implementing static analysis? Again, just a few seconds on the screen to give everyone a chance to respond. That's fantastic. So I think we've got a very reasonable number of responses here. There's lots of us online, but feel free to answer questions, ask questions as we go through, and I will be collating them, and we will try and answer as many as we can live at the end of the presentations. Okay, so with that, let's hand back over to our presenters today.
So, to give participants an idea of what we will cover in this discussion, let's have a look at the topics we are going to talk about over the next hour. We will look at some key organisational factors for achieving functional safety compliance for ISO 26262, the application of static analysis techniques from MISRA compliance to runtime error detection, recent ADAS cockpit application system developers' experiences with test automation and requirements traceability, and compliance tips from a functional safety certification body. At the end of the webinar, we will put your questions to our speakers in our Q&A session. That's a lot to get through. Now over to Steve Niemer from LHP Engineering Solutions.
Hi everyone, welcome to the webinar. I got an opportunity to present at SAE World Congress recently, and I thought I'd share those topics with you. Functional safety is a big topic for many people in the automotive industry these days, and I thought I'd present a few topics of how to implement functional safety, and specifically some requirements that are slightly onerous. So thanks for joining, and we'll get started. For the topics today, I am going to go through functional safety, but at a very high level, and I'll give an overview. I know many of you have very large documents, so you'd have to spend quite a bit of time going through it. But I think what's important is I'm going to pick a few topics out of it, a few requirements that really force change within an organization, and then I'm going to focus also on a software vertical. In the end, I think you'll see software is the biggest impact on functional safety and vice versa. I mean, you will spend quite a bit of time on software topics as it pertains to functional safety, and then the cost also, I think, and I'll reiterate that a little later, and I'll show you the examples. The cost also really is reflected in the software vertical. So let's jump right into it. So I'm your host, Steve Niemer. I've got quite a bit of background with safety critical application, and I think you can read it there, but the most unique, I believe, is that I've seen the implementation in multiple industries. I've seen it both in aerospace and defense and rail and in automotive as well. And now some of those have parallels, some of them have their own unique constraints. And in automotive, I think somewhat the most difficult given the numbers of permutations of cases for autonomous driving and so on. So safety is something I've been working on, product development, something I've been working on for over 20 years, and safety critical product development is something I've been focused on for quite a long time. And I'll jump right into the functional safety topic. If you look at the main page of the document, it strikes you immediately. There's a V. However, I actually see it as a W, which is interesting. So they give you a V for the hardware section, they give you a V for the software section, and then an overarching V. And when I see this, I think coverage. How are you providing coverage? How are you ensuring that you're testing the right cases and you're providing a safety case? And then that's what the V diagram means to me here. And then overall, though, there are things wrapped around it, like management and supporting processes, which are just as important, actually. So if we jump into, the specific topics, I'm going to go one by one and give you, one requirement out of the sections that has a pretty strong meaning and implication for you. I've lumped 3 sections together, 2, 3, and 4, and there's one line in the management section which says the organization shall create and foster and sustain a safety culture. That's a very, vague statement. However, the example I can give you is, when in a previous life, when a safety issue occurred in the field and there was human harm, the decision-making across the organization changed. As the head of R&D, I no longer had priority for development projects. The safety issue had priority, and the safety director managed those resources. So it really is about the decision-making that occurs within your organization when a safety issue occurs in the field. And that has a big meaning for a lot of people. I mean, I don't know that necessarily every organization has such a decision-making process. Startup companies, et cetera, they don't really have that set up right off the bat. However, larger organizations already have that. If you think about a workers' comp situation, there's a person responsible for that if someone gets hurt on the job, and that's an on-the-job injury. And there's an HR and a legal team that handle it to ensure that you comply to the regulations. Well, this is something similar to that, however, more on the engineering side of things than it is on the getting injured at the job situation. And another element I've pulled out is software architecture or system architecture. And if you read that statement, if an element is comprised of sub-elements, then and they're put in the same context, then they take the highest ASIL. What it really tells you is that if you've got safety features, don't combine them with your non-safety features. So the example I can give you is satellite radio and a braking system. You don't want those in the same processor. You don't want those on the same memory map. And if you do put them on the same memory map, then you're going to have to apply functional safety to both of them. So as companies are trying to make cars autonomous, there are companies trying to make autonomous cars, and there's a difference in that. Because if you do it from the ground up, you will design an architecture that handles the safety criticality in an efficient manner, rather than trying to slap, a sensor system on an existing vehicle and make the entire thing safe. It really does have an implication to how you architect your systems, and that's why I pulled this particular, element out of the document. If we jump into hardware, the one main focus of hardware and functional safety is the avoidance of single point failures. And, if I just use layman's terms, if a single thing fails, it doesn't cause a safety issue, right? And whatever that single thing is, the capacitor, resistor, the radio example, the tire bleed, whatever it is, single point failure does not lead to a violation of a safety goal. That's how the document describes it. And the entire section is really geared around designing hardware that avoids that. And once you've done that, and the mechanism in which you do that is kind of defined in the appendix, and they give you examples here like non-volatile memory checks and block replications, adding sensors, et cetera, and built-in test, which is more of an aerospace term than it is an automotive one. You're really driving software requirements, because once that hardware is actually out there, you're driving software requirements. So hardware, avoid single point failures, design an architecture that a software can actually add diagnostics to, and then obviously follow the V diagram model that you see on the page here, which is requirements to testing, standard process. Software. So software, quite a large section, very important, like I mentioned earlier, and again, the architecture discussion. If you combine software of different ASILs, of different safety criticalities, they all take the highest safety criticality. Again, a very painful statement. So What do you do about that? Well, design it so that you don't do that. Isolate your safety requirements, architect a system where you can do that, use external means for safety requirements. So there are many, many ways of handling that, but it is a very onerous one-liner, and that is very typical of any guideline. There are lines in there that, if taken as strictly as it's said, impacts almost everything in your system. And then on the right side there, you see that, from a unit testing standpoint for software, they want it tested in a real environment, on target. And they use the word closely, again, a guideline type word rather than a requirement or hard word. And it comes down to, can you validate your safety case? Can you justify what you're doing from a unit test standpoint? If you're only testing in simulation for some parts of it, if you're only testing on hardware for other parts of it, if you're testing at a system level, if you remember I mentioned coverage earlier, and you can make a case of that, then you've handled this requirement. But that also implies that you're managing your workflow, and it implies that you're managing your requirements and test cases in a tool chain. So again, like just one line, and all of a sudden we're buying tools, we're managing across the organization, we're talking to the systems team and the software team working together. That's all implications of that one line in the software section. A few more software requirements, some of them buried into the production section, right? So a procedure shall be defined to ensure the correct embedded software is put on your ECU. So just from a standard production process, they want to make sure that whoever's loading the code onto the vehicles or the ECU has got the right version. So it implies you've got a versioning system. It implies you've got a process between engineering and production and a change control board and all those things. But where this becomes very interesting is, what if software is ever changing in the field? So software is downloaded over the air. It has an entirely new meaning now. If you're going to meet this, then you've got to have quite a sophisticated system to be able to do that and still meet the intent of functional safety. And then in the middle here, the test equipment shall be subject to control and monitoring. And I've had this case, in many times in my career. I take a piece of software and I put it on one equipment and it passes and it works phenomenally. And I put a piece of software on another equipment, which is apparently identical, and it failed. And I find out later on that someone had modified something in the test equipment. So, and I think this is what it's getting at. It wants you to control both the versioning and the hardware software application of all the test equipment you have in your organization. Then on the right, the field monitoring process for functional safety incidents shall be planned in accordance to ISO 26262-2. They're pointing straight at the management section. And the reason they're pointing at the management section is because if there's a safety issue in the field, it changes the decision-making process. So it's not the same as an issue which is not safety related. And in your organization, is that a true statement? Or is it still managed by the same people with the same decision-making process with the same priority? So it's pointing at the management section from the production section of how they want field monitoring to be done. And again, that implies tools, implies process, implies training, implies management changes. So some key takeaways. Functional safety really is all about software. And I don't mean to demean or belittle any of the other parts. But if I were to put a similar, dollar sign as the Yelp reviews for restaurants, software gets $5 signs for coffee. And even worse than that, software V&V gets 5+. So anything you can do to make software verification and validation easier. So that's automation, that's standardization, and that's applying safety, right? At the front end, before this goes to the test team. Anything you can do from that standpoint will save you millions at the back end. And then in the end, the planning for all of this, the organizational planning and the management from the top is really the key to success. And that will define the winners and losers once a regulation comes out that implies that you have to actually implement this. As right now, it's pretty much set by the OEMs and the requirements that come into most RFQs, and it's relatively optional. There is no regulation right now that forces this, but I believe eventually there will be. So thank you very much for attending. I hope this has been helpful, and I hope to hear from you sometime soon.
Thanks, Steve. Now over to Pierre-Henri for a quick overview of hardware-in-the-loop
Thank you
testing.
very much, Steve, for this rather exhaustive speech about the functional safety compliance and its organizational, architectural, hardware, and software aspects. There is room to add a lot of more comments on the different topics you've covered, but I've decided to concentrate on the part of your presentation that deals with the test execution environment. As you've well said, Steve, the test environment for software unit and integration testing should correspond as closely as possible to the target environment. This guideline of the ISO 262 standard can be spotted in the notes that come along with table 7 and 10, which are dedicated to the unit and integration testing methods. Performing tests on the target environment is actually very important because it's the only one way to uncover the problems which are related to the hardware interfaces, the timing issues, the memory constraints, race conditions, RTOS services, and many others. To this extent, the avionics safety standard, the DO178B and C, which is the mother or the ancestor of most industrial safety standards, including the ISO 262, is very clear about the target environment. It considers target testing as mandatory and explicitly says that software tests need to be performed at least once in the operational conditions. That means with the final target environment. So, as a customer, as a user, you need to privilege a software testing architecture that allows you accommodating the various choices of compilers, CPU architectures, connectivity with boards and emulators, etc. By backing different build and execution environments into your testing framework, from the beginning, you are simplifying the later stages of testing. You are also likely to identify any target-specific bugs, for example, an endianness problem, earlier in your development. Thus, at the end, of course, you will be saving time and money in your project. The challenge for deploying tests to multiple systems can be simplified by using automatic tools that can build and maintain such a test framework that allows for switching the runtime environments. From a daily usability standpoint, it's important to consider a tooling that can take control, or even better, directly integrate with the popular development environments that are used for safety-critical software implementation. You can see a list of major IDEs at the footer of the screen. It shows the multiplicity of environments that needs to be managed. Knowing that, quite often, within the same company, you can find several IDEs used for different projects. So once your test harness has been properly built with your cross-compiler, executed on targets, your diagnostics and test results generated from the data coming out of the target memory will help you claim the certification credits that you need for your software verification. Let's consider now a reporting form in particular, the one for the structural coverage, which is well known as code coverage. Structural coverage is something that is mentioned several times during this webinar, as it helps a lot in identifying gaps for requirement-based tests, and it's also very useful to uncover dead code or unintended functionality. As we have seen just before, the modern test framework allows you to grab the code coverage results from different execution platforms. But not only. At QA Systems, we are aware that automotive customers need to get a complete coverage view across all the product variants that are generally managed through build variants of the code. Thus, we have developed a new build variant utility for the coverage measurement to improve the C++ coverage data for source code which is executed over more than one build variant. To do this, Cantata will detect your compiler switches, so H-defines, to separately identify the different build variants. The Cantata coverage viewer that we can see on the screen now will aggregate all the data for multiple build variants of the same source code. It's shown on top in the small code snippets. A specific build variant report can also be generated to summarize on the file basis the use of your preprocessing directives. This report is perfectly suitable as a certification evidence for all build variants of the source code you use for your projects. To conclude my comments on hardware-in-the-loop testing techniques, let's have a look at two methods in particular, which are again presented in the tables 7 and 10 of the ISO 262 standard, dedicated to unit testing and integration testing methods. These two methods are interface test and fault injection. It's commonly admitted that a lot of issues and bugs can be found at the code interfaces levels. Unit and integration testing can exercise the interfaces with both expected and unexpected values. Many interfaces in the embedded systems are programmed to ensure that parameters passed across the interface will be handled correctly to avoid data corruption or system failures. It's then important to ensure that defensive programming works correctly and produces the expected results. You can leverage the classical stubbing or mucking techniques, but you have as well the possibility to deploy a slightly different mechanism, the wrappers. Wrappers will not prevent the calls to the actual code or library functions that will still perform under the operational conditions. Like a stub, you can check the input parameters passed to the call, but as it is intercepting the real call, you can also check what is actually passed back from the code object. This is a major difference from traditional stubs, and it is particularly useful in the context of integration testing. Especially if you consider that wrappers can often offer the possibility as well to return whatever data you think to be pertinent for your test scenario. With this force return capability, the wrappers become an easy way to manage software fault injection. So instead of trying to configure your target environment to reproduce complex edge conditions, wrapper can help in the following scenarios, for instance. Modification of output or global variables to manage error triggering values, software alteration of memory registers and memory zones, such as RAM bit flips or corruption of memory mapped registers, disruption of software message content, so-called mutilation for message-intensive communicating systems, and many more that you can creatively imagine, I'm sure. So as a conclusion, testing on target is definitely a must-do activity in order to meet your functional safety requirements, and you need to set the proper infrastructure for it. Let's now move to the next topic and participant.
Thanks, Pierre-Henri. Now to hand over to our next guest speaker, Chris Clark from Synopsys.
Thank you for joining me today. My name is Chris Clark. I'm with a company named Synopsys. Synopsys is one of the world leaders in providing technology to the automotive industry with over 15,000 employees and 30 years of business experience, delivering solutions to a wide range of clients around the world. This range of clients spans all automotive industry tiers and allows us to have an interesting view into what are the new challenges and exciting technologies that are coming around the curve. Today I know we are going to be talking about 26262, specifically functional safety and static code analysis, but I do want to point out there are a number of additional solutions that Synopsys is able to provide both from a software perspective and a hardware design perspective. Now with that said, let's dive in. So where is the market going? We know there are a number of different challenges that the market is currently experiencing. It's probably one of the greatest revolutions in the automotive space in the last 20 to 50 years. But when we look at the automotive space, when we look at the vehicles that are coming to market today, it's obvious that there's a wide range of different activities, different types of systems, and different solutions that are on the market. It's not uncommon to see vehicles with 70 plus different ECUs managing a single solution or multiple solutions. One of the biggest trends that we're starting to see, though, is this thought or this convergence of software-defined vehicles. And this is actually really interesting, especially when we start talking about static code analysis, because of the complexity of some of these solutions and what has to be done in order to ensure that these different pieces of software that were once standalone pieces of software that are now being merged into single platforms behave in a manner that's expected. There's nothing we want to occur from a safety or a cybersecurity perspective when it comes to software. And there's a lot of players in this area. When we look at AUTOSAR, Automotive Grade Linux, AGL, Geneva, Red Hat, all providing different aspects and layers of this new software-defined vehicle. But from a Synopsys perspective, one of the things that we want to share with this group is how do we look at addressing not only static code analysis, but the overall challenges of reviewing what should you be looking for from a functional safety perspective when it relates to your static code analysis requirements and capabilities. At Synopsys, we look at 3 different aspects, and we call this triple shift left. This strategy focuses on 1, system development, where we look at the overall system from a functional safety perspective and ensure that we're able to provide customers and capabilities and help you understand what are some of the challenges that you need to address at the system level in order to ensure that your policies, programs, and specifically functional safety projects are engaged efficiently and appropriately. Second level is how do we look at software development? How do we accelerate software development so we're utilizing virtualization and emulation technologies to accelerate the overall program? And this does a number of things. 1, it helps us find problems earlier before we start baking hardware that has functional safety requirements in, and also gives us an early opportunity to address challenges and issues related to those software development practices. And then lastly, from an SOC development perspective, functional safety really has to have an adequate foundation in order for the software capabilities to function as expected. So from an SOC perspective, you have to ensure that you're picking not only the right software solutions, but the right IP blocks that give you a head start from a functional safety perspective in addressing not only functional safety, but cybersecurity and quality and reliability. And by doing that, we start to flatten the curve, the overall curve of number of defects and errors, and overall we get to 0 so that we are able to address the customer's specific needs around 26262. And in doing so, helping you as utilizers of different types of tools like static code analysis achieve those goals. Now, when we start focusing on 26262, there's 3 things we really start to derive and drive out of this: requirements, impact, and challenges. Requirements are easy at the surface. Your vendor is going to provide to you a number of different requirements. You're well aware of this process. It's an established process, but you have to derive as an organization what are the requirements that are downstream of developing or addressing this policy requirement or this product requirement that's been put in front of you. And that can be rather challenging as you start to translate that into static code analysis for proprietary code, static code analysis for open source software, and other third-party libraries that you may be utilizing in your solution. And really, this has a cause and effect from a hardware and software convergence standpoint. You know, when we look at the large distributed teams that we see that are both global and ethnically and quality from a quality perspective very different, and how you start to normalize those teams so everybody's at the same level and has the same capabilities and technologies. We also have to look at different types of languages. The world of C and C++ is starting to shrink, and we're starting to see more modern languages like Rust, Go, and others that are type safe and in theory provide a higher level of quality. Are they appropriate for functional safety environments though? And these are questions you have to ask yourself as you're developing these solutions. And as well as looking at significant adoption of FOSS or open source software, that is a huge challenge that is continually needing to be addressed in the industry, especially when you consider that open source software is very difficult to ensure that it meets functional safety requirements without a number of large exceptions. And then of course security, safety are critical. So how do you look at those from a decentralized system, decentralized development environments as a single system? And you start to see where some of these challenges start to really crop up. Now, I will say that from a safety, security, and coding standards perspective, normally most organizations are going to jump and say, oh, from a static code analysis, I have to address MISRA, I have to address AUTOSAR, but really most tools that you're looking at today are going to have those capabilities. Really what you need to look at is what is my overall process and requirement from a product development standpoint, and how do I ensure that I'm able to convey that information in a meaningful way, not only to my customer, but to all the developers when you're within your organization and outside of your organization that may have to touch or contribute code to the solution. So you really have to look at not only making a goal of assuring safety and security is delivered from our products, but also avoiding risk at multiple levels, from a functional safety perspective, a security perspective, and meeting market and regulatory or customer requirements. Next, when we look at our next goal is developing a product in accordance with safety and security goals, whilst delivering on-time high-quality features. Because of the market pressures and the times that we're starting to see from a product development perspective, that second triple shift left that I was talking about, where we start utilizing virtualization and emulation technologies to drive software development earlier in the life cycle, are becoming even more critical. So from a security and quality perspective and assurance activities and software development, these are absolutely key, and you have to take these into account. And then lastly are those coding standards we talked about. There's potentials for mistakes, and we have to address those. And in order to really look at them long term, we have to ensure those coding standards are codified in policy, but also looked at and managed from a lifecycle perspective for the overall lifecycle of the product. I only have a few more minutes here, but I want to touch on one important aspect, and that's open source. Now, when we talk about open source and we look at it from a static code analysis, we always find a wide range of issues. And one of the challenges that we really need to look at is how do we rate, manage, and view open source software, not only in a functional safety environment, but also from a quality, reliability, and dependability perspective. And really, that's where we recommend organizations take a much deeper look and focus on their approach with open source software. So with that, I want to thank you for participating. Thank you for allowing me to speak with you. And if you have any questions, I'll be happy to answer those. Have a great day.
Thank you, Chris. Over to Pierre-Henri for a rundown of static analysis and dynamic testing integration.
Thank you, Chris, for sharing your insights with us. Your intervention implies that an industrial software verification framework, willing to meet all the dimensions of functional safety verification, needs to include several tool chains. You need dynamic testing tools for unit and integration tests, as well as proper solutions for static analysis, but it may as well include tools for profiling, worst-case execution time, memory usage, etc. Being tool vendors, we have a responsibility to ensure that these ecosystems of tools can collaborate and work together. At QA Systems, to ease mutual integrations, we have decided to develop Eclipse plugins. The Eclipse IDE is a proven environment for simplifying collaboration between tools. Every vendor can develop its own set of UI perspective and views to present the user with the relevant data structure, information, and visualization. The user can access all the generated information and underlying metadata without having to toggle between interfaces. There is a legitimate use case for synchronizing static and dynamic testing verification when the user is in front of his IDE. Indeed, let's imagine that you've just developed some functional tests to cover a given requirement of your safety critical software. At this occasion, the tests fail and you detect a flaw in the software design. You make an attempt to fix the source code, and then you rerun your tests to check if they are passing this time. And your test run is successful. But you can't immediately check your modifications in, because you need to ensure in parallel that the modified code does not break some MISRA rules. So having the static analysis information generated at the same time you build the dynamic test harness for the modified code is very handy in order to enforce compliance with the MISRA standard. If you detect MISRA rules violations, then you have to iterate again on your code to find a suitable implementation that is still successfully verifying your functional requirement, but at the same time respect the MISRA rules as well. It's a matter of agility between the two types of verifications that talk to each other via the synchronized build and analysis. In Cantata, it is managed via hooks in some customizable makefiles, which allow invoking as a pre-built condition the coverage analysis in order to gather the required static analysis information. So again, when modifying your code, both dynamic and static verifications are triggered to guarantee the consistency of your test results and the validity of your source code modifications. It's now time to move on with the next topic and participant.
Thanks again, Pierre-Henri. Over to Anne Packery now from Faurecia Clarion.
Hello, my name is Anne Packery. I am the Functional Safety Team Manager for Faurecia Clarion Electronics Europe. Our products range from cockpit electronics to display technologies and advanced driver assistance systems. Some of the most challenging aspects of my recent project have been to ensure the complete traceability of safety requirements down to the software low-level design, and by this I mean being able to track them down to the code itself, and also to ensure the completeness of the validation and verification strategy at each stage. I have in mind the unit testing, software integration testing, and software validation, and after system integration and system validations. Relying on a tool which can offer bidirectional traceability visualization on both V-cycle legs can be very powerful to support the creation of validation strategies that can satisfy coverage and cost effectiveness. In that way, functional safety team can support from the very early stage of the project and guide efficiently the architecture choices with a minimal set of tests, and also during the design stage it helps us monitoring the implementation rate of the functional safety requirement and associated safety mechanisms. Complete traceability is also very important during the stabilization phase when we want to be quick and efficient in corrections, and we have at the same time the need to ensure the integrity of the functional safety concept. Creating a set of functional and dysfunctional tests that we can automatically play for each software release will help securing the correct implementation of the safety strategy. And having the visibility of the requirements in the test tool is definitely a plus to understand the purpose of some tests and to quickly narrow down the impacted requirements when something is going wrong during testings. By controlling complete traceability of software requirements and verification and validation activities, we have a very powerful process to verify the coverage and provide V&V analysis report to contribute to the safety case. If supported by a qualified tool, the use of automated verification and validation procedures can definitely help saving time and money. As mentioned, during fast-paced and technically complex projects, it is often challenging to keep this traceability and make sure we perform the right tests at the right moment. Therefore, I always encourage a test-driven development approach in order to secure that the test design will meet its purpose. I also recommend to rely as much as possible on the quality assurance tools and procedures. Most companies in the industry are following automotive SPICE guidances, which can very efficiently support the ISO 26262 verification and confirmation needs when we align the processes. Thank you for your time. Wishing you a nice webinar and interesting conversations.
Thank you, Ms. Packery. Over to Pierre-Henri, who will give us an overview of automated requirements-based testing for ISO 26262.
Thank you, Bethan, and thank you very much, Ms. Packery, for sharing your experience regarding the need as well as the difficulty to ensure the complete requirements traceability with the software low-level design. All of that with the intent to demonstrate the completeness of the software verification. So, requirements-based testing is indeed a key activity required for the compliance with the ISO 262 standard. Looking at the standard, requirements-based tests are highly recommended for all safety integrity levels. First of all, for the embedded software testing. This is the table 14 of the chapter 6 of the standard, but as well at all ASILs for unit and integration testing, as stated in table 10 and 7. In the chapter 9.4 of the section 6 of ISO 262, which is dedicated to requirements and recommendations, you can find specification about the use of both requirement-based test coverage and structural code coverage. These two forms of coverage are related but distinct, actually. Requirements coverage, in the context of verification, measures the degree to which requirements-based testing has verified the implementation of the requirements. Its purpose is to demonstrate that test cases fully verify the requirements with which they are associated. Structural coverage, which is known as code coverage, measures how much of the code has been executed by tests according to a given metric. ISO 262 recommends using structural coverage analysis to help in achieving full requirements coverage. It indeed helps identifying gaps in the requirements-based tests, and it's useful to uncover inadequacies in requirements or dead code or even unintended functionality. Requirements and structural coverage evidences are required or highly recommended by most safety standards, and not only the automotive ISO 262. It's shown in these tables, where 100% of requirements coverage are always requested starting from the lowest safety integrity level. The degree of code coverage metric will vary upon the safety integrity level. Starting from 100% of functions entry points for the ASIL A of ISO 262, for instance, it jumps to 100 modified conditions and decision coverage for ASIL D. So being in a situation to meet these coverage targets represent quite a lot of work. Hence the challenge pinpointed by Forestia Clarion and the need for some automation. Given this context, it's not surprising that industrialized methods for automating requirements-based testing is one of the most requested testing solutions from the functional safety market. Modern code analysis techniques and tooling now allows automatic test generation from the source code. But this is only practical in the context of ISO 262 requirements-based testing if, first, such a process generates an optimal number of test vectors for executing all branches of your software. Second, test case generation is exhaustive enough to achieve the expected coverage metric, like the MCDC for the ASIL D projects, for instance. Third, generated tests are easily readable and maintainable. Even if you use a proper automatic test generation to fulfill these criteria, any auto-generated test case from the source code still need to satisfy the software requirements. Thus, it requires human insight and experience to assess that the generated test cases guarantee on top of that their traceability with the low-level requirements. However, test tools now can provide a framework in order to make tracing tests to software requirements a lot quicker and logical. At QS Systems, we are developing a test solution named Cantata, and it delivers such a framework to ensure the bidirectional traceability between new requirements and the tests, even if, or shall I say especially if, they have been auto-generated. First of all, software requirements can be imported from any requirements management or ALM tool using several formats, like RECIF, which is the standardized requirements inter-exchange format, or simple comma-separated value files, CSV files, or Microsoft Excel formats. Once imported, they are displayed directly within the dedicated Cantata trace view, where they can be associated to generated tests. This association process can leverage manually designed tests, but they can leverage as well the Cantata autotest feature, which performs automatic test case generation from C and C++ source code. These auto-generated test scripts will contain a set of test vectors in order to exercise all possible logical code branches at a given coverage level, like the MCDC, which is required by ASIL D. These tests will include as well an English language description that justifies the tool decision to pick up specific test vectors for exercising a particular decision in your code. Once associated, the traced associations can be exported back to the requirements management or your ALM tool, along with the pass-fail status for each test case and the total code coverage achieved by the test scripts. This exported trace data is stored in your requirements management tool and may be part of your ISO 262 software verification report. So, with the appropriate tooling, you can achieve a complete three-way coverage analysis. First, measure your requirements coverage along with the associated test results directly from within your requirements management tool. Then get visibility on the coverage of the tests to ensure that there is no unexecuted or failed tests. By the way, the corrective actions can be taken as part of the regression testing activities that you may organize in a continuous integration system. Finally, you can fill testing gap thanks to the code coverage measurement. At this time, you may as well uncover testability issues and the need for refining existing or even crafting new requirements. So as a conclusion, automated requirements-based testing in the context of ISO 262 functional safety should bring a lot of value to your software verification activities. Let's move on with the webinar and the next topic.
Interesting points. Thank you, Pierre-Henri. Now over to our last guest speaker, Gudrun Newman from SGS.
Today's session is about software verification according to ISO 26262. Welcome to all. I'm Gudrun Neumann. I'm Product Manager, Functional Safety Software and Team Leader Functional Safety. I'm working for the SGS TÜV SAR. The SGS is the Société Générale de Surveillance. The headquarters is in Geneva in Switzerland. It is a world leader in testing, inspection and certification. SGS TÜV SAR is a joint venture between SGS Group and TÜV Saarland e.V. The Global Competence Center Functional Safety is in Munich. All around the world we have expert teams for functional safety. We are accredited test and inspection body for functional safety and cybersecurity. We are a member of relevant standardization committees like IEC 61508 or ISO 26262. Our services includes functional safety assessments and audits, also certification of safety processes, components and systems can be provided. Especially for software and software tools, we are assessing whole systems, subsystems, or components. Let me talk about our experiences as assessors. Verification by automatically testing, also called regression testing, is very often used. Here we recommend to add the appropriate requirement IDs to each test case to ease the traceability. And add also a short description of the used methods for deriving test cases and the test method itself. This way you avoid discussions with assessors. We want to see examples and also maybe you avoid manually filling of tables. Also software verification reports are created automatically very often. Here we recommend to add the level of integration to the test results. That delivers an evidence of the execution of the required test phase and also eases manually documentation or makes it subfluous. Also, please achieve at least the detailed results of the release tests. So you have an evidence of the original test results available and that increases the confidence in your test protocol summary in case someone is asking. At last example, I want to talk about the non-acceptable verification results, which must be analyzed and a rationale for acceptance must be documented. Examples could be static code analysis, e.g. MISRA violations, structural code coverage metrics lower than 100%, failed test case results. Here describe the reasoning for these deviations or what kind of process is applied and add the according bug or issue ID. Thanks for your attention and have a successful verification.
Thank you, Gudrun. Over to you, Pierre-Henri. What's your take on certification?
Thank you very much, Mrs. Neumann, for sharing with us your experience as an assessor for software functional safety projects. As before, I will add further comments to some of your messages, following the ones about requirements traceability, which has been already discussed during the webinar. I've been particularly interested by the mention that repeating tests again and again can be superfluous. As a best practice, I interpret that as don't get everything driven by the end deliverables because of the certification pressure. In other words, don't always spend the time and efforts to get every bit of the certification evidences every time you run your tests. Simply make sure, as you say, that you archive at least the detailed results of the release tests. As a customer, you may want a balance of the general information extracted from your test results, not just for certification, but to make sure your tests are working correctly and diagnose them when they're not. So this is the diagnostic dimension of test results. For instance, test reports can be used in intermediate project phases for management status or for analyzing a set of tests that are impacted by a change in the code. To my eyes, such a flexibility on archiving and reporting test results can be obtained at its best within a DevOps or continuous integration, continuous delivery framework. Within a DevOps pipeline, you can implement continuous unit and integration testing. Tests can be run and reported automatically every time code is checked in to verify new or modified code. To fit into a DevOps pipeline, your testing tool needs to offer the following. First, a comprehensive command line interface. Then, test scripts and test cases need to be generated in clean editable code in order to guarantee repeatable deterministic results every time you build and run your unit and integration tests. Third, an API with access to your test inputs and results data. Finally, the option to generate open standard files for third-party tool integrations, such as SonarQube for dashboarding purpose. All your tools options must be available from direct command line invocation, lending itself into automation in scripts, makefiles, batch files, and Jenkins declarative pipelines within a DevOps or CI/CD framework. Then Mrs. Neumann was pinpointing the need to justify all verification deviations, such as coverage gaps, failed tests, or MISRA violations. If we consider the analysis and documentation of these deviations when a testing tool is used to support the verification, it needs obviously to be backed by a process. Such a process is generally part of the information contained in certification kits delivered by tool vendors. Such kits must include a comprehensive safety manual, as well as comprehensive instructions on how to use the tool for particular objectives within the standard. All of that to simply understand the boundaries of the verification activities processed by the testing tool and manage the non-acceptable results and deviations to deliver the proper justification. If you are interested in the tool qualification process that gives you confidence in the use of software tools, you need to refer to Chapter 11 of the Section 8 of the ISO 262 standard. For the Cantata tool, every major release gets certified, and SGS TÜV is evaluating our tool development process and documents to ensure that no deviation is found in regard of the requirements of MIFOD 1C described in Chapter 11.4.9 of the ISO 262 standard. As a consequence, Cantata is certified as usable in the development of safety-related software according to the ISO 262 up to ASIL D. Provided that, of course, you follow the safety manual, installation and user guides information, as well as all the defined use cases of the ISO 262 standard briefing documents. All these documents are included in the certification kit provided to our customers for every release of the tool. Testing tool certification kits are delivered along with standard compliance certificates issued by accredited certification bodies like the SGS TÜV company. Choosing a testing tool that comes with a third-party certification is the guarantee to save all the efforts and costs related to the in-house qualification of verification tools. Indeed, why put the burden on each individual user to reinvent the wheel on something which is proved? This concludes my last comments about the final webinar intervention. Thank you.
Thank you, Pierre-Henri, and thank you everyone for interesting presentations there. So we'll take a few minutes just to revisit the poll that we conducted at the beginning of the session. So we asked a few questions and we got lots of responses. There are many of you online. The first question that we asked was, which is your biggest unit testing challenge? And we can see that there's quite a spread there. I don't think we can kind of glean any definitive answer. There seems to be a spread of issues that the people are facing. So feel free to reach out to our experts online there. The next question that we asked was, who in your organization is responsible for functional safety? Not so much of a spread there. Quite a few of you have a functional safety manager that you can turn to, which is great, but interesting results nonetheless. And the final poll question that we asked was around static analysis. So that was, what is the biggest barrier to implementing static analysis? Again, it's a reasonable spread there. I think different people are hitting different issues. And again, it's good that we've got experts that we can turn to answer those questions. Okay, so thank you for all the questions that have come in during the lectures that we watched. I'm not sure that we're going to have time to get through all of them today, but we'll try and answer a few of them live. So if I open the floor to our presenters, can everyone turn on their webcams and mics? Can we hear you?
Yes, Adam, thank you.
Great to hear you, Pierre-Henri. And do we have Chris?
Yes, I am here. Thank you.
Fantastic. And how about Steve? I noticed Steve was having some connection issues during the session.
I'm here. Hi.
Excellent. Hi, Steve. So if we start with a question that I think would be more directed to Steve, which was, what kind of physical equipment is used for the verification of software?
Well, I mean, obviously, like, developers have integrated environments that they use. So obviously, that's the most basic of equipment, the environments you're using for development. But then, you know, there are a slew of companies that develop test equipment where you can integrate your ECUs into, you know, hardware in the loop systems or just open loop systems. And, you know, we're partnered with a company, National Instruments. There's many other companies, DSpace and many, that develop just interface cards to be at least access some of the pins and some of the functionality within your controllers and your software via hardware. So
Okay.
that's the kind of equipment we use.
Yeah, no, that's great. So there's a question around static analysis here. So I guess that's more in Chris's realm. It says static analysis has been around for many years, sometimes with mixed impact. What are the best practices or most important factors to implement static analysis into the software development lifecycle?
Yeah, that is actually a common question that comes up, because most organizations, when they get a static analysis tool, they turn on all the tool and all the features of that tool, expecting to accelerate how they're going to reduce the number of defects in their software. And what ends up happening is they actually create a massive backlog, and that backlog actually has a lot of false positives or other issues that are introduced into the pipeline. And you start to get this disenfranchised view of what static code analysis is. And really how an organization should look at this is make a determination of what do you want to address in the short term, and turn on those specific features to address those challenges, and slowly mature your static code analysis model so that not only are your developers understanding and able to handle the types of issues that are coming in, but they're also able to mature their code from a safety and security perspective with static code analysis over time.
Okay, that's great. And there was a question that came in during one of Pierre-Henri's segments. Can you tell me more about Autotest for automatically generating tests in Cantata? How does that actually work? Pierre-Henri?
Yeah, that's a nice question. Indeed, it's a smart piece of our tooling, and it brings a lot of value in the automation of requirements-based testing. So in short, Autotest is capable of generating test cases to get the maximum code coverage. at the selected coverage metric. So it can be, for instance, the MCDC level, which is the most stringent coverage level for the ASIL-D of the ISO 262. So with this aim, Autotest is traversing the logic of your code and will be automatically setting the data to values that will increase the theoretical coverage it has achieved. It can actually mutate all the data values if the initial choices are not improving the coverage. To do this, it will leverage the stubbing and wrapping capabilities we have already discussed in order to exercise peculiar decisions and branches of the code logic.
Excellent. That sounds great. I know I've seen it at work. It's really effective. So there's a question here. Interesting to me. C and C++ has been the mainstay language of embedded systems. Do you see any other languages coming to the fore? I think Chris, maybe that would be more appropriate for you.
Sure. We've actually seen quite a few new languages coming in, but even some of the old stalwarts that you typically wouldn't associate with either a functional safety project or something of a high security or high safety requirement. So, we've seen everything from Perl to Rust, Go, some of the newer programming languages that are coming up for rapid prototyping, and then they go back and convert those into C or C++ to meet specific needs. But again, organizations need to balance what their workforce is and what that workforce is comfortable with, and then make a determination from a prototyping standpoint what actually will go into production. So, it's not reasonable to assume C and C++ are going to be going away anytime soon.
Okay. Scrolling through here. So, what are some of the ways to lower the workload of functional safety? Steve, do you want to field that one?
Yeah, sure. I mean, I think I mentioned the planning, right? There's a decision making that has to happen up front across the board, not just in software, but any kind of automation you can do, and any kind of tool integration you can do. So right now, the tools out there, they provide a lot of functionality. But if you're going to be buying more than one, and you will be, whether you span quality, your management, and obviously the software tools you see right here, you've got to integrate them. And if you integrate them well enough, you can launch test cases automatically. You can populate your results automatically. You can do differences automatically. And every step you take then actually improves the workload, because it's really functional safety in every industry is really a manpower problem. And original solutions, is offshore, throw a lot of bodies at it. It's very inefficient, and it's actually caused many issues, and it allows lots of good test cases on that process. But automation, I think, is the key, especially in automotive where the permutations are infinite. I don't think there's any way to achieve autonomous driving truly without like some kind of innovation in process and tools.
Mm-hmm. Yeah. Okay. So we've run over slightly, but I think let's just squeeze in one more question. So this one for Pierre-Henri, I think. You've mentioned several times the Cantata certification kit for ISO 26262. Is that at a cost?
So I will pass a very positive message here. All the Cantata tool certification kits are available to our end users free of charge, as long as their maintenance contract is active with the company. And it represents a real value for the customers, knowing that the self-qualification of verification tools, like it is done for every safety critical project in the aerospace industry, where you need really to requalify the tool you use, is very well known as time-consuming and thus a very costly activity.
Okay, very, very good to know. Okay, so I think our time is up. Thanks again to everyone that's joined us today. If you'd like to find out more, our organisers will contact you after the webinar, and there will be a short survey on what you thought about the webinar. Please fill this out, as it will help improve the quality of the content for future events. So thanks for watching, and goodbye. See you next time.
Thank you.
Thank you.